诺贝尔就是lecture，让你写 summary。
真好，真好，你这已经赶上博士生的。我那个中国同学，天天就读论文，写summary，然后最后再做。
差不多，我们现在上课也看到。
这个博士生的套路。
可以啊。三叉戟。
La travailler de maison. I'll be up there. Come on, stop.
First name, last name,
You know that. Today, I'm going to talk about a couple of things involving chapter 3. Is that where we are? Asymptotic equipartition. Have you heard of Chebyshev? Chebyshev. SHEV. Inequality. It says that the probability minus mu greater than Chebyshev inequality says that the probability of x minus mu is less than or equal to sigma squared over delta squared. What that says, it says the mass outside of mu minus delta and mu plus delta, mu being the average. That's the expected value of the random variable x. So the mass outside this interval is less than sigma squared over delta squared. Okay, do you know what this means here?
So the possibility of mass outside of that range is
Yeah,
small.
the mass outside this interval. So here's mu. And this is mu minus delta. And this is mu plus delta. Mu is the mean. So that says that the mass, the probability mass outside this interval that's what this says. This calculates the mass outside of this interval. That means the mass here and the mass there. Does that make sense? It says that it's less than delta squared over sigma squared. Well, if delta is equal to sigma, then this says that the mass outside is less than 1. Well, that's kind of obvious, isn't it? Right? So if this happens to be sigma plus delta, and this is mu minus delta, this is mu plus delta. You know, when you have a mean there, it's always kind of confusing. Let me write it with no mean value. So the probability that x is greater than delta is the mass outside of the interval minus delta to plus delta. That's what this is. This is the probability that the mass how much mass? That's the probability of the mass outside. That is so there's that line. Say this is y and this is x. And so this is the line y equals x. This is the line y equal to x. So the probability that y is greater than delta corresponds to that integral, the integral of the mass probability that x is greater than delta is equal to the integral from minus infinity to minus delta of x, of minus x, right? F of x dx plus, I think we're calling these p of x, plus the integral from delta to infinity of x, p of x dx. That's the mass outside that interval. You agree to that? And so that is equivalent to integrating here, which is this integral, which is this integral, and integrating here, which is that integral. Right, so the integral from right there, this is the absolute value of x, isn't it? Right, because like x is minus 1, minus 1 is a plus 1. So that is just the, this is just the magnitude of x when x is negative. This is the magnitude of x when x is positive. Is that too trivial? No? Not? Okay, good. What I'm going to do is call this J minus 1 and call this J1. So this integral here is J minus 1 minus, it could be minus 2. And we'll just call it minus 1, call that one plus 1. And this, of course, has a mean of 0. Now, the expected value of x squared is equal to sigma squared when the mean is 0. And so we break this up into the same integrals, minus infinity up minus infinity to minus delta x squared p of x plus this integral from minus delta to plus delta plus this integral from delta to infinity. Right, so I'm splitting up the integration of the expected value into 3 integrals. One is about from minus delta to plus delta, and the other is the integral outside. Now, I claim that this is less than, no, this is greater than minus infinity to minus delta plus integral from delta to infinity, right? Because this is not zero. This middle integral is not zero. That integral is greater than zero. And so therefore, if I drop it, this thing here, this means that sigma squared is greater than that integral. Greater than the sum of those two integrals. Sigma squared is greater than or equal to minus infinity to minus delta x squared p of x d of x plus the integral from delta to infinity p of x dx. Now, this means that x is going to be x squared is going to be larger than delta squared, isn't it? This x squared, it's from delta to infinity, so it takes on values greater than delta. So I would say this is greater than or equal to, and I'll just write it down here so you can see it on the same page. A squared minus infinity to minus delta p of x dx plus a squared from delta to infinity p of x dx. Because this is always greater than that. So that means then that these two integrals are greater than these two integrals.
Professor, what is A stand for?
What is
what is A?
delta?
A square.
Oh, I beg your pardon. It is not a squared. I don't know why I put a squared. Even my notes here, delta squared. She's quick. And so what is this? So we've got two. Sigma squared is greater than or equal to delta squared times two integrals p of x dx. One goes from minus infinity to minus delta. And the other one plus delta to infinity, p of x dx. But isn't this just the area outside? So that's just delta squared times the probability that x is greater than delta. And so there is Chebyshev. X greater than delta is equal to sigma squared over delta squared. So if delta is 1 sigma, then it says the probability is less than 1. That's not very strong, is it? Right? Kind of weak probability. But suppose delta is 2 sigma squared, 2 sigma. Suppose delta is twice. Then that means the probability of the mass outside, that is 1/4.
Yeah.
See? So what is that Chebyshev telling you? It says how much mass is outside, say, values of the variance or the standard deviation, right? Sigma is called the standard deviation. And so if you're outside 2 standard deviation, the probability, the mass out there is less than 1/4. So that's not bad, but if you're at 1 standard deviation, that's not very good, is it? So how good is Chebyshev? How good is Chebyshev? Well, let's take an example. Maybe this is where the A came from. Here's an example of mass density. So 1/2. So sigma squared is equal to 2 times and so I integrate from 0 to A. What happened? I didn't do anything. So how good is Chebyshev? Let's take that delta there, that delta some point. But first let's calculate sigma squared. That's 2 times x squared times the probability density. It's 1/2a dx. And so this is equal to a squared over 3. So the probability let's now calculate how much mass is out here. without worrying about sigma. So how much mass is outside that interval? Talking about that shaded area. So the probability that x is greater than delta is equal to the integral from minus infinity. Well, there's no mass out there past a, to minus delta, and 1 over 2a dx. 1 over 2a is p of x, uniform density, plus delta to a, 1 over 2a dx. And so this integrates to 1 over a to a minus delta 1 minus delta over a. And this, of course, is for delta less than a. See, that the length of this, that length is just a minus delta, isn't it? Right? This shaded thing is a minus delta. And so the area is a minus delta times 1 over 2a. It's a shaded area. And same as that. And so the answer comes out 1 over a minus delta, which is 1 factoring out a gives you 1 over 2. And so this is what the probability looks like. So here's 1, goes down like this, and this is delta over a, and this is 1. Delta over a is 1, right? There's no mass outside. There is no mass. If delta is greater than a, there's no mass out there. But Chebyshev says the probability that x is greater than delta is less than sigma squared over delta squared. We just calculated sigma squared. It's a squared over 3. And so I get that this is equal to 1/3 1 divided by, since I'm plotting, delta over a, right? And so Chebyshev is coming in like this. This is Cheb. That's a Chebyshev approximation. The total as a function of delta over a, right? So if I'm at 1, right, if delta over a is 1, this should be at 1/3. So this is not quite right, because this is 1. So 1/3, something like that. Here's, right. So this is Chebyshev, and this is actual mass. Right. This is Chebyshev approximation. This is the actual computation.
Professor, we
Maybe-
should add a square in that result. It's 1/3 multiplied.
Well, that's I want to put 1/3 when delta,
Why not?
when delta over A is 1,
No, it's
Chebyshev says 1/3.
yes, 1/3 multiplied by that result add a square.
Oh, yeah, you're right. Right?
Yes.
But if delta is equal to which means A, right? If delta is equal to A, that's when this thing goes to 0. Then that number is 1/3. But then if you go out 2A, it drops to 1/3 times 1/4. Right, so 1/12. So it's better, right? So Chebyshev is okay if you get out several standard deviations. Otherwise, not so good. Okay, let's see. Autodash. You know, I told you you could find the solutions to that homework problem, right? Or at least the first one on the web. Oh, look, we go straight to termite. By the way, the go back one to 8371, and you get cover solve. See that? Cover solve. Solutions. So there's your homework problem. Is that what you got? So here we are at asymptotic equipartition property. Oh, there's Chebyshev's inequality. There's Markov inequality. Here's Chebyshev. And it says, show this. Supposed to prove that, which we just did. And there's more interesting stuff there. But I want to look at oh, there's a piece of cake. I want to look at problem 7 in the textbook. So, a discrete memoryless source emits a sequence of statistically independent binary digits with probabilities. The probability of a 1 is 0.005. Not many ones, right? The digits are taken 100 at a time, and a binary code word is provided for every sequence of 100 bits containing 3 or fewer ones. Right. So we will develop a code that corresponds to a string when there's 3 or fewer ones. Right, there could be 0 ones. There could be 1 1. Right? How many in a code? A stream of 100. By the way, you think 100 is long? How many bits are there in Hello World? Hello World. HELLO space WORLD period. $12 bytes. 12 times 8 is what? Right, it's close to 100, isn't it? So Hello World's got 100 bits. Right. So 100's not very long, is it? How many bits are in Shanghai?
Too many.
So, what we're going to do is build a compression. In other words, we got 100 bits here, and we want to compress the bits so that we don't have to send 100 bits, right? So if I have a stream coming in, here's 100 bits, okay? I don't want to send out 100 bits. Now here's another 100 bits, send out another 100 bits. I want to take 100 bits and compress them to useful information. And so the question is, how many words are there in zero, one, two, or three ones? Okay. How many are there of 0 ones? Isn't it just one?
Yes.
Or 100 zeros, excuse me, right?
No, one.
100 zeros is part of the, we want all words with 3 or fewer ones. All the words, that's 0 ones, 1 1,
One.
2 ones, and 3 ones. So how many words have 0 ones?
One.
How many have 1 1? How
100.
many have 2 ones?
No.
4,950.
Well, he says 100 here, that, and that. Right. So these are how many words. Right. Now the question is, what's the size of the word that can take care of 166,000? How many words are there in the 100-bit thing? Oh, there's a lot of words in 100 bits, right? But we're not going to take all hundreds. We're just going to take ones with 3 or fewer. And so these are how many we need to worry about. If I have 8 words, how many bits do I need? To take care of 8 words, how many bits do I need?
64.
3. 0, 0, 0, 0, 0, 1, 0, 1, 0. Right. 2 to the 2 to the 3 is 8. 2 to the 3 is 8. So 2 to the something is equal to this. That's how many bits I would need to take care of that many words. Oh, here's typical. There's our friend typical. Let's run typical. Do that one. That one, I don't need that one. I'm gonna build a table. Here's a binomial. That's just a bunch of numbers. We'll use that one. Here's a Boolean expression. Here's typical. So I'm going to take epsilon. I'm going to take epsilon equal to 0.1. For example, I'm going to take n is 0.005. Oh, 05. Okay, so let's see what we got here in the set. I think we ran out of space here someplace. But look, here's the probability. I mean, 0.065. 0.065 is the probability that you have 0 ones in the 100 bits. Right, that's just 0.995 raised to the power 100. So that's what that number is there. And I think I didn't run that thing here, the bool. Let's just see if anything is typical here, and I'll run the bool thing. And so bool gets run, and it probably won't complain now. Oh, look, there's true. You know, we probably need true, don't we? I don't think there's anything true down here. I'm not sure, but you know, 100 is a long ways down. See, that's all false. But look at, I told you there was a lot of words. How many is this? Is millions. This is billions. This is trillions. I don't know what's above trillion. Well, we got a long ways to go. Those are what you call big numbers, aren't they? Nevertheless, they're not typical. Okay, so here we go back. And I'll make that, let's ease it up a little bit. 1.11. Oh, it didn't do anything, did it? Okay. I'll do 0.2. 0.2. Oh, see, we picked up, okay, this is, the number for 3, right? 3. This is 2. That's 1, that's 0. Right? Ah, look, that's a typical set. That's a typical set.
So Professor, what is the meaning of that? The typical is true.
It means that there's a range there, you know, between h of x plus epsilon. And-
H2P minus epsilon.
Yeah, another one is, well, that was the P, the M, right? Remember M? Remember M here? 2, H2 of P. By the way, H2 of P would be H2 of 0.0005, right? So that's H2 of 0.005, still probably a small number. But N's 100. So we got everything we need there. Now, how much probability mass is in those things?
Professor, if you increase,
Right, how much, we know how much mass this one's got, right? It was 0.6 something. You multiply 100, you got 100, you got to add up 100 of the cases where there's 1 0. Right. And then you got 5,000 cases for 2 zeros. Right. And you got 160,000. Okay, so he says here, here's the mass. This, you got 100 of those, right? You got 5,000 of those. You got this number, see, still small, right? The probability, that is, you add up all those numbers, and you get that. But look at this, 0.998. That means now, if we devised code word with only those, with only this number, the probability of error would be 1 minus this. You know, so I start with 100 words, and I'm going to send a lot fewer words, but I have to realize that there'll sometimes be an error. That is, if I compress this stream of hundreds, see, got hundreds coming in here, 100 bits, over and over and over and over and over. And I only code those words with 3 or fewer ones in the stream, and then I send it out. But I find out that there will be an error. The probability that would be an error would be 0, 0, 2. 0, 0, 2. That would be the probability that there's an error in. So that's not much to pay for compressing 100 down to how many?
3, 1.
Well, we need to say 2 raised to some power is equal to that number. Okay, here it is, log 2 is equal to 18.
Professor?
Right, 2 raised to some number is equal to that. That is 2 raised to the 18 power is that number. So I took 100 bits, compressed them down to 18, 4 times, and I'm only going to pay a small error, a small probability of an error.
If we change, what is epsilon? Because if you change epsilon, then everything,
Well,
everything is fixed.
in this particular problem, it doesn't matter. I mean,
But if we change,
all epsilon does is it picks a value for a typical set. We don't know yet what a typical set's good for. We're just introducing the concept.
Okay.
but the probability of having 3 or less ones will be changed if we change epsilon.
No. In this case, it's
Oh,
not true. We could add another, we could take 4 zeros, right? 4 ones, we could include 4 ones in the code. So that adds a lot more.
Yeah, so if
Right, the next one up is gonna be a pretty big number, isn't it?
Professor, I mean, if we increase epsilon, then the number of ones possible increase, and this
Yeah,
number
well.
will change.
Don't confuse epsilon now with this problem. Let's see.
So it's just the concept of typical, but without.
See, there's, if we take now, this thing's got 4 million, 4 million words there. So you take 4 million, that's more than all those put together, right? These numbers, they grow pretty big fast. By the way, typical set. Here's the set of everything. This is chi. And then here's a typical set. A and epsilon. The typical set always is always in chi. Typical set is in chi, the set of everything. By the way, look how many numbers here that all the things you put together with 100 bits. All right. That's maybe that's more information than there is in the world. So if we take all the books in the world and compress them, there probably wouldn't be numbers like this. What about 1,000? 1,000 bits. Ooh, look at all the. We could quantify everything in the universe. Now we may have trouble with the debt, right? We may have trouble with the national debt. By the way, you know the debt, the national debt keeps increasing, right? Doesn't it? What happens when the debt starts going faster than the velocity of light? Maybe we got a problem, huh? By the way, there used to be a saying, if I told you this joke before, then you can laugh again. That the physical review, the number of pages in the physical review was getting bigger and bigger and bigger, right? And so a person calculated the bookshelf, how much bookshelf you need to start stacking the physical review in, and found out that, the bookshelf is going faster than the velocity of light. Said, oh, but don't worry, because there's no information in the phys rev. I didn't hear anybody laughing. So we have then we have this sequence here, right, and the probability of error. And so what he does here, you know, we built our compressor, right? Because every time we see a word, we have 100 words coming in, and we know the locations of the ones, right? And so that goes into a word we send on the transmission. So we got 100 words coming in. We have to work with them to find out how to code. In other words, this particular string goes to a code word, right? And we have 18 of those, 18 bytes in the code word. So that you could use a computer to do the matching if you wanted to, right? So you got 100 bits coming in, you send out 18. 100 bits into, okay, you have a data here, you take 100 bits and you compress it. So that means if I have a file that's a megabit, then I compress it down to 250 kilobits. 4 times we compressed, because we got 18, but we started with 100. And the probability of error is so small, I probably don't even worry about that. Okay, so here's, in case of Chebyshev, he's got Chebyshev coming out here to be less than 0.04, right? I told you Chebyshev's not all that good, right? Because we already know what the probability of an error was, which is 0.002, right? That's a lot better than this number. So the bound is much larger than the actual probability. So Chebyshev, sometimes okay, sometimes not okay.
So it's just approximation?
Yeah, just approximation. It's kind of a weak approximation, isn't it?
But what is absolute here in this Chebyshev? Absolute.
What, that top equation?
Is the absolute equals to delta? It's different formula.
Oh, he takes epsilon 3.5. That's a different epsilon. then that determines the typical set. Okay.
It's just after
That bound is, so sometimes it's good, sometimes it's not. Sequence.
So, Professor,
I'll start on this, but we won't be able to do much. We only got about 5 minutes.
so we use Chebyshev. We use the approximation of Chebyshev only when we cannot compute the probability of error. When it's too difficult to compute it, we just find the
Well,
value.
you know, Chebyshev is probably useful for cases where you don't know much.
But we know the variance.
Well, we calculated though. You got to calculate the
The variance.
yeah
I
of,
mean,
of that. Right, you got to calculate the variance of the distribution. Well, we've done that for Bernoulli processes, right? Series of.
yes.
A sequence. X1, X2, X3, X3, comma, Xn. That's a sequence. I'm gonna flip a coin, right? Flip a coin, that's X1, right? Flip a coin, that's X2. Flip a coin, that's X3. Flip a coin, that's X4. So those are IIDs, aren't they? But here's the question. Xn goes to X as n goes to infinity. You know, if you take a frog and you put a frog on a diving board, and the frog jumps halfway, will he ever reach the length? Will he ever fall in the water? He only jumps halfway. Will he fall in the water? Nope. Won't fall in the water. But what is the limit? It's the end of the board. So he jumps the first time, he covers half the board. Jumps the second time, covers 3/4 of the board. Jumps again, he covers whatever. So I flip the coin. I get a random variable. Flip the coin. Flip the coin. What is the sequence converge to? That's the question. Or can we even find what it converges to? Well, we say that mean square mean square convergence, MS, is when the expected value of xn minus x squared goes to 0 as n goes to infinity. Keep in mind, we don't even know what x is here. Right? We only know what the xn's are. We don't know what x is. There's another type of convergence in probability. And convergence in the probability is when the probability that x minus xn or xn minus x, whichever you want to take, is greater than 0, greater than delta. By the way, what is this? What does this thing say? There's no mass. This is the mass outside delta, isn't it? That, we say that goes to 0 as n goes to infinity. That's called convergence in probability. So far, we don't know what that means even. So we got 2 minutes. So next time, I'm going to cover a couple examples here of convergence. This information pertains to the chapter 3. So read the beginning of chapter 3 of the text. I'll give you homework on Wednesday. Okay.
Yeah, me too.